Okay. So, log entry 1100 hours. The USS CF push runs silent and steady. Operators trusted to hold course, running apps, binding services, requests flow, dashboards glow green, databases echo back like sonar in the dark. Yet beneath the surface, unseen pressure begins to build. First a few background jobs, then a slower query. The CF database feels the strain. The CF API keeps working, unaware of the growing pressure below. Then alarms, response times spike, requests pile up, logs blur with warnings, visibility drops. The hull of the USS CF push shutters. One more search and the pressure might become too much. With this short teaser, welcome to our talk, Below Operating Depth, Observability in Cloud Foundry API and Databases. My name is Johannes Haass. With me today is Pascal Zimmermann. And yeah, we've chosen a submarine theme for our talk because operating Cloud Foundry can feel like navigating deep below the surface, quiet, steady, and unseen, as most users never see the machinery that keeps Cloud Foundry running. Also, it's a bit like in submarine movies like Das Boot. It's about staying calm when the pressure rises. In this talk, we'll share a few real-world incidents where the CF API was pushed below its safe operating depth, and we cover not just what broke, but also what signals mattered and what we learned along the way. Our focus is less on the bugs themselves. What matter more is to spot the right signals, how to react before small issues cascade, and how to steer clear before the pressure becomes too much. Pascal and me are both software engineers at SAP. We are active in various working groups of the Cloud Foundry Foundation. Pascal is mostly active in the foundational infrastructure working group, where I myself am mostly active in the app runtime interfaces working group. We've been working with Cloud Foundry for many years now and have seen quite a lot during that time. So let's look at the first incident. It was a Wednesday afternoon, 1600 hours. The day shift was starting to wrap up. It was a usual day, all systems steady, until suddenly the background job queue of the CF API spiked. Not a big deal, we have seen this before. Bugs in scripts, CI jobs running crazy, load tests by users, and so on. Our first reaction, add more workers. Surely, if we added more power to the engines, the queue would train faster. But, however, this time it did not. The queue stalled, the pressure kept building, the database, already strained by the queue length, began to choke under load. Within minutes, response time collapsed, the CF API went down, and no CF push was possible. The USS CF push was pushed beyond its limit. Let's have a closer look here. So what happened here is a user deleted a handful of apps. So far, so good. And because of some special circumstances related to those apps and a bug in the CF API, those delete requests triggered hundreds of thousands of blobs.delete jobs in the background. Those blobs.delete jobs were still being processed, but only at a very slow rate of 10,000 jobs per hour. So if we have a queue length of 100,000, we would have needed roughly 10 hours to process the whole queue. Also, we noticed that the blobs.delete jobs have a priority of 0, which is the highest priority in the background job system of the CF API, meaning that any other job, for example, the jobs resulting out of a CF push, have practically no chance to get picked up, and therefore we have a CF push downtime. As already briefly mentioned, our first reaction was to add more workers, so we have a faster processing of the queue. And we've also decided to lower the priority of those blobs.delete jobs because clearly a blobs.delete job is not as important and can wait a couple of hours. But the update statement for the priority ran forever. The CF API database, which was already under stress, was now overloaded and job processing came to a complete halt. After then looking into various dashboards and different solutions, we finally decided to scale up the CF API database to a bigger instance type and restart it. This gave us more database resources, and with this, the job processing kept going again, and we were able to process the remaining roughly 90,000 jobs in about 30 minutes. And once the whole queue was processed, the CF API was fully available again, and CF push recovered. So that's quite a long time frame. probably you cannot read it, but the total duration of this incident was about 4 hours. So there was 4 hours where users were practically not able to do a CF push. So what did we miss? How could we have reacted better? For that, let's look at some database metrics. Hope you can see it well, but I will say all the important numbers. If we look at the basic metrics like CPU and memory, they looked all fine. CPU increased a bit, but it was like around 10%. Memory percentage also increased a bit, but it was went only up to 40%, so there was still quite a bit of headroom. Active connections was stable. IOPS had a few peaks, but was still within a to expected range. But the real danger here was database storage. That's where the hull of the USSCF push was buckling. Let's zoom in a bit. So as you can see, the storage of the database kept slowly increasing, making queries slower and slower every time, until eventually they took practically forever once the storage of the database was fully consumed. Once we then scaled up to a larger database instance type, we also got more storage and higher IOPS. So we had more storage resources available, and this then finally got the job processing started again. Okay, so what did we learn from this incident? Well, first of all, in the beginning, we didn't watch the right dials or the right metrics. We thought, because the queue was so full, we thought this is the root cause why the CF API is not fully available, why CF push is not working. But that was not correct. The real bottleneck was the database I/O and storage saturation. And therefore, our first reaction to add more workers was, first of all, a wrong choice, but it actually made the issue worse, because with adding more workers, we even increased the database load further, which got the whole job processing completely stalled. Scaling up the database wasn't, of course, cheap, but in this situation, it was the only move forward that could stop the USSCF push from sinking. In that moment, stability mattered more than anything else. Observability, in this case, helped us quite a bit. I mean, we had all the information we needed during this incident to analyze the issue, but it was, in some ways, a bit too much information, so we had to figure out to look at the right metrics. But once we focused on the database I/O metrics, we understood how the database was overloaded and that only a scale-up of the database can save us from this situation. Our metrics in the aftermath also helped us to get a clearer view why and when queries slow down, especially when the database is under load. So what can we take away from this incident? First of all, if you remember, the initial incident was caused by a bug in the CF API, which created those 100,000 blobs.delete jobs. We fixed those bugs to prevent this massive job creation in the first place. Next, the query which caused the highest load during this incident. This is a select for update query, which is used by the CF API to fetch for the latest jobs. And this query can be very expensive, especially this for update part. And we basically got rid of this for update part, making this query much cheaper, especially if the database is under heavy load. Internally, we've updated our scaling scripts and guidelines to ensure that the CF API database has always enough storage available and that we don't run into such situations again. And finally, we've also found out during the incident that the queue length metric is not necessarily enough because it's just a snapshot of what is in the database. It doesn't show you what is actually being processed. So for that, we added new metrics to this CF API for the number of processed jobs and how long the job processing or how long it takes for one job to complete. Yeah, this was the first incident. However, this was unfortunately not the only time the USSCF push was tested under pressure, and Pascal will walk you now through another case.
So let's discuss and check out the second incident. A log entry Thursday, 1400 hours, the day shift was back from the lunch. all systems are ready until suddenly the query execution time spiked up and we've got high CPU load. So it's also today landscape or environment update day. So in general, the incident is related to rolled out query optimization. We faced the issue inside an ongoing environment update. We've introduced a distinct on query to optimize the service instances and the service plans. The query are complex to the CF roles and the service plan visibility. Let's start with the symptoms of this issue. We faced a massive increase of the CPU utilization over the time, as you can see here. And there was already a rolled out optimization based on the query that handles the service plans. And there was this is the corresponding old query. So you can see here, previously there was a distinct inside this query, and this was generated then by the Ruby source code. And after the optimization, you can see here that there's a distinct on and the corresponding service instance ID inside the query itself. So we've identified that the query planner calculates the execution time for the query on large environments slower in another way as on small environments. So that means you've got the case that on small environments, this query works well, but on large environments, it's the case that the execution time is higher than on the other environments. This fact results in slower execution time of the query, and it's also the fact that this corresponding change was rolled out upstream, and the CF performance test worked well while testing the optimization. After we've identified the root cause of the issue, we've discussed a potential deep fix on live environments. So how we solve this. We've decided to update the query on the prod environments on the fly by executing the corresponding Bosch commands. So this results in a corresponding for loop over all API nodes. Then, as a second step, we're using Bosch commands, especially the SSH command, to establish a connection to the corresponding node itself, because it's necessary to fix that on time on a live environment. Otherwise, we've got problems, and our customers are deeply impacted about this. And the last corresponding step is definitely to use sed to modify the corresponding Ruby source code and also roll out the corresponding monit command to perform the restart of the cloud controller. And as you can see, as a last point, we are also embedded a sleep, because otherwise it's the case that these corresponding jobs are executed in parallel, and that should definitely not be the case. So what are the lessons learned about this issue in general? Watch the right metrics, embed predictive alerting is one big point. Because predictive alerts reducing the analyzation time of issues. So it was the case in this corresponding issue that we've analyzed that directly after we faced the corresponding alert for the CPU, and then we've checked the query execution time. And as a result, we directly identified, oh, there's an issue with this newly provided query optimization, and then we've got the idea to just fix that on an environment. Then, second step, not all usage pattern can be tested on development systems. Because the query change and the decrease of the execution time was deeply connected to the environment size and the usage pattern in general. And, of course, we've also faced the case that the database query planner can differentiate between the major versions. So, in general, I've just checked the source code of Postgres 15 and 17, and there are definitely optimizations for the query planner in version 17. So that means this corresponding issue is not available anymore on PG 17. It's only available in version 15 and 16. And also takeaways, as I've already mentioned, for these corresponding issues are definitely, you should check the corresponding Postgres version in general, and also check the release notes of it, and add additional tests for the database version itself to check really the performance of this case. It's also the case that the corresponding cloud controller colleagues add additional Postgres version in their CF deployments, CF performance tests. Let's check out the incident number 3. Let's talk about the third incident. Log entry Monday, 2 p.m., all systems are ready until the job total queue length increased dramatically. The incident covers the service deletion, but the connected service broker did not respond for more than 60 seconds. The previously rolled out optimization helped a lot to safeguard the issue and to cover the issue without a real impact for our customers. Background of this job is definitely that a customer rolled out a corresponding execution script to delete service instances, and it was the case that the service broker have not reacted in time. The script only tried to delete the instances without any confirmation if that works or not. So as you can see, the total job queue length increased dramatically, but with this corresponding optimization that we've rolled out beforehand, you can see that only the storage percentage increased a bit and the CPU percentage increased for the database itself. So this corresponding metrics are the corresponding, the upper metrics are the corresponding database metrics, and the lower metrics are the cloud controller metrics. So as you can see here that the job process jobs increased, but the CPU percentage and the storage percentage are stable. And the corresponding beforehand previously embedded optimization for the dynamic job priorities and query optimization in general helped a lot to handle this issue in time without any real impact for our customers. So well done, team. We deserved the outage and we faced no real impact for our customers. So let's summarize the corresponding stuff in a mission debrief. I'm not sure if you're aware, but if you got in a sub mission, then there's a mission debrief at the end. So let's summarize this. Our key findings for the Cloud Controller API that should be monitored are the outstanding queues, the job queue lengths, the new metrics job duration seconds, and the job pickup delay in seconds. On the database side, we've selected the classical metrics CPU, memory, IOPS, read and write, and also the storage percentage. And of course, we've also rolled out a few more corresponding changes to the community. We've embedded a few query optimization and in general refactoring, and also new indices, especially for the corresponding job queues. And of course, Johannes already mentioned it. Johannes also prepared corresponding PRs to add new metrics for the cloud controller itself. So thank you very much for visiting the below operational deep observability in Cloud Foundry API and database talk with us. I hope you had some fun with us. You can reach the people behind this feature in the copy and in the integrated database Slack channel. And if you'd like to connect to follow up, you can find our contact infos here, and of course also our socials. If you're still curious, we are happy to deep dive into your questions.